quarks under strong force. The analysis of the patterns of the hadrons we have noted was systematized in the whiskily named Eightfold Way of the US physicist Murray Gell-Mann, who introduced the concept of the quarks. All hadrons are made from the quarks. Baryons contains 3 quarks and mesons contains 1 quark and 1 antiquark. Very recently, new structures have been found deep in the interior of the island, which 2 quarks and 2 antiquarks, tetraquarks and 4 quarks and antiquarks, pentaquarks, extremely ephemeral. The internal structure of these objects is subject of the ongoing exploration. Yep. The properties of the hadrons come from the quarks they contain, and the way they are bound together by the strong force. When Gell-Mann and the Russian-American physicist Georgy Zweig first introduced the idea of the quarks, all the known hadrons could be arranged according to their octet and decuplet patterns, and where there are gaps in the patterns, the expected hadrons were later identified experimentally. The position of the hadron in the Eightfold Way simply arises from which quarks it contains and in which directions they spin. Many of the faster decaying hadrons do so because the quarks inside them fly apart in the different, more stable combinations. All of the summaries some of the best evidence for the existence of the quarks. They can be used to predict the existence of new hadrons with a particular change, spin, mass, and so on. It has become clear that a hadron island is strongly linked to another land mass to the southeast. The Isle of Quarks is our next destination, and we will travel by train. The strong force takes us directly there over an imposing railway bridge. Wow. Just as the electromagnetic force is carried by photons, originating in the bosonia and traveling the road network far and wide, the strong force is also carried by boson. This boson that trains on our tracks is called the gluon. It glues the quarks together inside the hadrons. It glues the quarks together inside the hadrons, and also sticks the protons and neutrons together inside the nuclei. Wow! It is this force which overcomes the electromagnetic repulsion between the photons. The strong force equivalent of the electric charge is called color charge using the US spring. Since it has US spring means COLOR. Okay? Since using the US spring, since it has nothing to do with optical color and was named in the America. It was named this way because there are 3 colors of the quark that, when mixed together, leave no net color. Yes. Because the addition of the 3 color, the primitive color, makes white. Yeah. Just as the 3 primary colors, three prime colors mixed together to form white. Yes, I'm correct. Quarks have color charge, and so do gluons. In analogy with QED, quantum electrodynamics, for an electrodynamic. In the analogy with QED for electromagnetism, this theory of the strong force is called quantum chromodynamics, QCD, and it is with QCD that all the calculation and prediction for hadronic properties and for most of the behavior of the quarks and gluons have to be made. Using QCD, it is possible to calculate important features of the strong force, such as the way it changes with distance. It is also possible to get information about the masses of the hadrons. Those masses are mostly due to the binding energy of the quarks and the gluons, and the fact that they are whizzing around so rapidly inside the hadrons. Not only is the strong force strong, not only is the strong force strong, it does not get weaker with the increasing distance. Wow. The electromagnetic force and gravity both fall away as the square of the distance. Yes. Laws of a square, right? So if two objects are moved farther away by the factor of 2, the gravitational or electromagnetic force will fall by a factor of 4, not so for the strong force. Not so for the strong force. At two quarks are pulled apart, the strong force between them remains constant. This means that a huge amount of the potential energy builds up in the gap, and at some point there is enough of it to produce new quark, anti-quark pairs, as if from nowhere. The quantum vacuum contains little loops of the particle antiparticles pairs similar to those we saw affecting the magnetic moment of the electron. Making such a pair into a real pair of the quarks and the antiquark can mean that the strong force has to stretch over a shorter distance, and that reduces the potential energy. So, because quantum mechanics allow it, and the result lowers the tension, these pairs will indeed be spontaneously created. Wow. This is weird and important because these new particles then stick to the original quarks, making new hadrons. In other words, you have to put in so much energy to separate quarks from each other that you end up making more quarks. Wow. This is frustrating if your goal is to isolate a quark. Many experiments have searched in vain for isolated quarks. In vain. However, as the two quarks get closer, the strength of the force between them actually drops. This is what happens as we moved eastwards across Hadron Island, upward in the energy scale. Remember, a short distance means higher energy. Atomland was characterized by the binding energy of the several thousand electron volts. The nuclear binding energy on the west coast of Hadron Island are thousands of times higher, many millions of the electron volts, traveling eastwards amongst the hadrons. We reached an energy scale of great importance at around 200 million electron volts. This was where we crossed the bridge between Hadron Island and the Isle of the Quarks. Wow. Around this energy scale, which is known to be localized by the strange name of the lambda QCD, a change in the physics takes place. On the northwestern side, quarks are effectively invisible, hidden inside hadrons because of the weird pair creation behavior as you try to pull them apart. But to the southeast, the energy level has increased to such an extent that we start being able to resolve the quarks inside the hadrons to see them in their natural habitat. What we see is that they are moving around quite freely because they are very close together, and the force between them is relatively weak. As we travel east and the energy scale increases well above the lambda QCD, the strength of the force continue to decrease, and we can begin to explore the Isle of Quarks in ever more detail. Thank you.